Okay, so again, momentum's relationship to force. We talked about this a little bit on Friday. Today, what we want to do is I want to look at Newton's second law a different way. Okay, so Tyson Zimmerman was a student of mine back in 2022. He graduated in 23. A smart kid. He thought he wanted to go into engineering. He was in my one semester class. I said, Tyson, you really should be in the full year if you want to go into engineering. But regardless, he looked at these concepts that we're studying and we're talking about, and he was a deep thinker. And so I was going through this concept of momentum, and he says, Mr. Eisinger, so is momentum sort of like potential force? And I thought, very interesting way of thinking of it. And I asked him if I could put that down here, sort of give him credit for that. He said, yeah, that's fine. He actually holds the record still to this day for the most efficient egg drop device. So these devices that you guys are going to start building at the end of this week, he still holds the record for the one that was the lightest weight, the smallest in size, and that protected the egg. And so I used a little ranking system. He was pretty clever on how he designed this. And so he still holds that record. Anyway, he was talking about momentum's relationship to force, and I'm like, well, thank you for asking that. You'll see that there is a strong connection between momentum and force, but it's not just force. There's a time value. So I want to show you again how to reformulate that impulse, that theorem that we looked at. Newton's second law. One of our most foundational laws that we would study in this class. We show that force is related to mass, but also how rapid the change in motion is. I'm going to go ahead and replace that A, just like I did last time, with a delta V over T. And so this is very similar to what I did on Friday. But instead of thinking of that as the rate of change in momentum, which is what we talked about on Friday, I'm going to multiply both sides through by T. And I have now something that instead of writing force is equal to m times a, what I have is force multiplied by a time interval is equal to m times change in velocity. Another way that we could write that force acting through time is equal to the rate of change, or not, is equal to the change in momentum. So it's a reformulation of Newton's second law. Many kids will find A to be confusing, right? A is a confusing quantity, but changes in momentum are relatively easy to understand, whereas A is a little bit harder to describe. What this equation says is force acting through time. So force multiplied by time interval is equal to the mass times change in velocity, or another way to say that is that we can define force in time as a new quantity called impulse. Those things multiplied together is this quantity called impulse. And what impulse does is it changes an object's momentum. So this theorem is called the impulse momentum theorem. It relates forces multiplied by time to changes in momentum. So when Tyson said, so momentum is sort of like potential force, you can see that momentum is in this equation, and so is force, but it's more than just force. We have to have a time interval. And so, like, what's close, but we have to include time. So time plays an important role. Now, what I'd like to do is do a variety of examples with you today to try to show you qualitatively how this works. We're trying not to do a lot of math with this. So this is mostly about understanding how two things multiplied together can change momentum. First one I want to look at is this thing called the impulse momentum theorem related to producing a large change in momentum with a small force. Now, I'm going to do a variety of demonstrations. One of those, I don't know that I've used my air cannon yet with you guys. Have I had this thing out yet and showed you guys how this thing works? Not at all yet? Okay, so today, if someone would be willing, I need to get this thing pumped up with some air, and I'll show you how the time interval can play a pretty significant role in changing the momentum of the object that's going to shoot. So we'll show you that in a little bit. How can I have a small force produce a large change in momentum? Quite simply, just by having that small force act through a very large time. So if I can change the amount of time that I have that force acting, I can produce a large change in momentum. Now, you don't have to write a lot of stuff down. The bottom is showing how that time can change momentum by making that time bigger. I get a bigger delta P. All the 4 pictures up top are showing how the time increase yields a larger delta P. If it acts for a long time, I can get a fairly large change in momentum. I want to go in reverse on this so we can finish by looking at the cannon. The picture on the right, I want to take a moment and talk about what this is here. So that picture right there is something called a solar sail. And it's not exactly the same as the way a sail would work on a sailboat. A sail on a sailboat would use the wind to be able to exert an impulse to change the momentum of that boat. What this one is talking about is using solar winds, so maybe the winds from the sun, essentially just small ejected particles, to be able to exert an impulse to, like an asteroid. And so recently, if you guys might pay attention to this stuff in the news, you're like, oh my gosh, big asteroid going to strike the Earth. There's a chance that it's going to strike the Earth in 2032, and they keep increasing the percentage. So it's likelihood now to be like a 3% chance that it hits, and they're calling it like a city killer and stuff like that. So I don't know if you guys pay attention to that stuff, but NASA's constantly monitoring these things, and they're looking for asteroids that might be on a collision course with the Earth. Raise your hand if anyone knows what I'm talking about. A few people. All right, so it's in the news. So one of the ways that NASA is sort of trying to figure out how to protect our planet from asteroid collisions is by doing something like a solar sail. They could dock a little, not a wind sail, but a solar sail on the asteroid, land on it, put something there that can deliver a small force from the sun, but for years of time. And so if I have years of time to change the momentum of an asteroid's got a lot of mass, and they're moving really fast, right? So we're concerned, like, oh my gosh, it really wreaks some havoc. But if I have a long time, then I can exert a small force for years to be able to slowly change the momentum and get it off course so it doesn't collide. That's an idea of the solar sail. Now, if you're a baseball player, hockey player, anyone that uses like a racket or a club or a stick or anything to exert an impulse to a ball or a puck or whatever it is, the coaches always say follow through, right? Follow through. And the idea there is that if I can extend the time, I'm not going to actually swing at you, but if I were to extend the time of contact right from there through there, if I can make that time bigger, I can get a bigger delta P, get that ball to go off faster. So extend the time. Raise your hand if you've ever been on a cruise liner. Raise your hand if you haven't. Jack, would you mind sharing really quick? What were you on? Where'd you go? What'd you do?
I think when I was like young, like 5, we were on a Disney cruise.
A Disney cruise? Do you remember it?
Yeah.
Okay. You were about that, right? I've never been on a cruise. I'm not a big like motion sickness guy. I mean, I would suffer from that, so I've never been on one. But I've heard stories that these things are like small cities. And I would imagine on this Disney cruise, Jack, you probably had 5,000 plus people or so. Probably a lot of young kids. That would definitely be not my scene there. But anyway, pretty loud, but a lot of people on that city or on that boat. I've heard that the captain of that ship would have to start hitting the reverse throttle, right? And so instead of driving the boat this way, it's going to go into reverse to try to slow it down. It might need half an hour to 45 minutes to stop that boat. And that's just simply because it's got a huge amount of mass. Traveling on the seas at maybe 20 knots, they're like, oh, we're going to come into port. If they don't hit the reverse throttle half an hour, 45 minutes before they get to port, that boat's just going to go right into the land, right? So you need a lot of time to change the momentum. Last one I want to use with my air cannon. The long barrel of that cannon extends the time to be able to allow the ballistic, the thing that's being shot, to come out faster than if it were a short barrel cannon. And so the idea behind that is I'd like to take this thing here and sort of do that demonstration. I need someone that would be willing to sort of pump this up for me. And so anyone willing to get a little exercise today, just got to exert some force acting through a time to be able to pump this thing up a little bit. I'm sorry, folks, we have to have only one person. I can't have everyone volunteer. No, really, oh, just, I appreciate you doing that, Ian. Come on up. So I'm gonna have you pump this thing up here. Now, while you're getting this ready, because it takes about 3 minutes or so to get the air pressure up to the right value, I want to share a couple of stories with you. So it is sort of like a bike, but I have like a bicycle stem there. Now, what Ian's going to do is he's going to pump this up to 25 psi. That stands for 25 pounds per square inch. I want to share a quick story with you. Many years ago, I had students building contraptions to launch eggs outside for my 4-year class. And I allowed them to use compressed air. So a kid made something like this at home. And instead of using a bicycle pump to pump it up, he said, well, let me use my air compressor. So he used his air compressor, put that up, got it up to about 80, 90 psi before the thing, when the thing finally ruptured, and it did, the PVC pipe ruptured. Liquid behaves different than air. So if it ruptures under liquid pressure at 90 psi, it just becomes like a little squirt that comes out and then the pressure quickly goes down. If it ruptures under air pressure, what happens is the air goes through that small opening and expands rapidly, because that's what gases do, and then it blew the entire thing apart. And he almost lost his ear because a piece of shrapnel came and almost took him out. So we don't want to go any higher than 25. Okay, no more than 25 psi. Oh my gosh. Okay. I'm going to back away a little bit. You guys right in the middle. If you guys, I'm going to shoot this thing down the center aisle. Thank you. Yeah. So thank you. I'm going to shoot this, but I don't have anything in it right now. So what I'd like to do is I'd like to shoot a ballistic. So in this case, I'm going to shoot a ladybug. Now a ladybug doesn't have a lot of mass to it, right? So even if this thing comes out and hits you, it's not going to hurt a whole lot, but it can deliver a little bit of an impulse to you. So now for this guy, I'm going to leave him right at the end of the barrel. Now, what I'm going to do is I'm going to limit the amount of time that the compressed air can exert force on this thing, and that should limit how fast this thing is going to come out. Now, Ian, I appreciate you doing this, tossing this thing. He's okay with being right there. This thing could deviate a little bit right towards you there, so we don't want to do that. This thing does have a laser sight, so I want you guys to see that laser sight. So that's where this thing would hit. If there were no gravity, that thing would come out of this, and it would travel in a straight line right towards that spot, and it'd hit right there. So when we press this button, now where's Ian? You did the work. I'm going to let you shoot this thing. So come on up. Yeah, thank you. All right. Now, you want me to catch it?
Yeah, sure.
Okay. Now, just. Oh my gosh. Okay. Now just the button where it says the button right there. Don't press it yet. This is a solenoid valve, and so a solenoid valve is common to take electrical energy converted into mechanical motion. So when you press that button, it uses a 9-volt battery to open this valve very rapidly. It's going to shoot that thing out. Now I'm going to stand over here. I'm going to try to catch that thing because I am a trained professional. So I'll try it. Protect Austin here in case it goes awry. You need to hold the base of that thing. Oh, you just aimed it toward me. Right. You need to hold the base of that thing. I'm going to try to hit the button up top. Nope, up top, the laser.
Yeah.
Nope, up the laser.
Right.
Right there. No, up.
Oh, yeah.
Yeah.
Sure, I got it.
I just want to make sure my hand's in the right area.
Oh.
Do it again.
Oh, yeah. Well, oh, there you go.
It's not. Okay. Okay. I'm good. I'm about ready. Okay. Are you? I'm good. I got my hands.
Gravity's gonna, you think it's gonna go down?
I don't know what's going to happen. Okay. Are you ready?
Yeah.
You may count it now.
3, 2, 1, go.
Oh, okay. Now, it came out pretty quick, right?
Yeah.
But how can I make this thing go off faster, do you think? If I extend the time interval to make that thing not just act that small little time here, but actually have it act throughout this entire thing, would you guys agree that's going to make the time bigger? That should make the speed coming out quite a bit greater. Now, I'm going to have you pump this thing up. There's still some air pressure in here. So we're going to keep that in there, and now what I'm going to have you do is I'm going to have you pump it up again to 25 psi. We're going to push that thing all the way to the back. Where is that? No, don't go to 30. Don't go to 30. Okay, let me help you a little bit with that. Yep, you got to push that thing in and then pull that bar up. There you go. All right, 20. Now, look, I would like to go to 30, but that would change two variables then, right? Because we're going to change the time by pushing it back, and I change the amount of force. Then I don't know the impact of the time, right? So we're only going to put it at 25 psi. Ian, later, if we have time, we can put it to 50 psi and just like. Jack wants to try to catch it.
I don't know about catching it, but
All right, so 25 psi. Raise your hand if you've ever shot like a black powder rifle. Black powder? Have you done it? You know it? So the important thing about black powder rifles is you want to make sure that the shot that you put in is rammed all the way home, right? All the way back. If you have an air gap between where the gunpowder expands rapidly and where the bullet is, if it can't push directly on the bullet, it's going to push on the barrel of the gun, and that could cause it to blow up, right? So you really want to make sure that during like that kind of rapid expansion, that you have the object right next to it so it can push. You have that 25 psi? That's it there? Okay, this is going to come up. It should come up a little faster. At least that's what the theory says. Now, this time, what we're going to do, Ian, I'm going to have you ram this all the way back. So you take that push bar and push him or her all the way to the back there.
I don't know.
Yeah, that's okay. You're working on becoming a trained professional. Push that all the way back. Okay. Yeah. So what we're going to do is we're going to greatly extend. We're going to extend that time. I'm not sure if you got it. I got it. Verify it. What we don't do is we don't look inside the barrel. Right. Okay. 22. Yeah, that's good. All right. So that's 22 inch compared to like 1 inch from before. This thing's really going to come out. That thing has fins, and it can just like go off like that. So, just are you ready?
Are you ready?
I'm a little scared.
It's okay.
All right. Last time it landed around there, didn't it?
Yeah.
Okay. You can get rid of the laser.
I'm gonna
You can
go
get rid of the
on.
laser.
I'm gonna go on go. Okay.
3, 2, 1, go.
Yeah. 3, 2, 1, go.
I mean, could you guys tell it came out faster?
Yeah.
I still missed it. I'm usually pretty good at that. But yeah, what I've done is I've increased the time interval, and that made that speed greater. Okay. Get rid of all that error. Yeah. So there's still some error in it. It came out so quickly that it left the barrel by the time the air had already or still had air back in. All right. So there you go. Low demonstration. Thank you. How about 2 claps there for Ian? Thank you.
So if we put the 50 1 years over.
Yeah, so interesting question. What Ian said, if we put it to 50, it still wouldn't use all the air because at 25, it still had air pressure left. But the amount of force acting would be about twice as great initially than what we had, just because if you think of pressure as pounds per square inch, it's force per square inch. If I double the amount of pressure, so instead of 25, it's 50, I'm going to have a larger force, probably for a similar amount of time. It's actually going to probably be less time because it's going to accelerate more rapidly. But it still would have a larger driving force, which means I'm going to get that thing to come up faster. Okay, so it still wouldn't be like twice as fast because I don't use all of that to begin with, but it's certainly going to increase that. Okay, so demonstrations, key to seeing the physical concepts. It does take some time, so that makes it a little bit less efficient, but it's important for you to see. Okay. Oh my gosh, I'm video recording this too, so you missed it. If you weren't here, you missed a really cool demonstration. All right. Now we're going to look at one more set of slides here. Another interpretation of the impulse momentum theorem. This one says for a given change in momentum, if delta P is the same, then force and time would play inverse roles here. Now, oftentimes students will be confused between these two slides, the most recent one and the one that we're looking at now. This one is talking about the change in momentum being a constant. The other one was talking about the force being a constant. I want you to see that these are two different things that are constant. For this slide, the force was a constant value. The amount of force that I'm exerting is a function of the person swinging the bat. The amount of force I'm exerting is a function of the number of propellers and how fast they're turning. The amount of force being exerted is the amount of gunpowder I put into that thing. The amount of force exerted is the force from the solar winds. That force is a constant, so all we're doing is we're extending the time to make the change of momentum bigger. For this one, what I'm saying is that delta P is the constant. If that car is going to come to a stop and it's got momentum coming into braking or into a car collision, the same delta P occurs. It's going to take away its momentum. If the same delta P occurs, so that change of momentum is a constant, then a small force acting through a big time would produce the same change in momentum as a big force acting through a small time. You notice now the thing that's constant is delta P. The thing that is variable is the force and time, and they play inverse roles. Making one bigger makes the other smaller. So anytime things are inversely related, an inverse relationship means if one thing goes up, the other thing goes down. That's what it means to be inverse. Increase the time, make the time bigger, that makes the amount of force smaller. Now, I have 3 or 4 different examples up here, just to show you where the impulse momentum can qualitatively explain what's happening. If you jump off the tabletop and land on the ground, you should bend your knees when you land. And the reason for that is that what that does is it greatly increases the amount of time it takes for you to come to a stop, and that lessens the amount of force acting on your legs to stop you. So you wouldn't want to land stiff-legged, you want to land with a little bit of cushioning. When you build your egg drop device, the big time acting through a small force is going to keep that egg from breaking. Now you're not going to drop it into a pillow. You're going to provide that pillow, if you will, for your device. So that's going to make the force smaller. If you have that thing come to a very sudden stop, you're going to experience the same delta P, but that egg is going to experience a really large force because it's going to come to a sudden stop. So you're going to try to design some sort of cushioning system in there. On Friday, I had Brody showing the video of boxing. Now, Brody, you were hitting a, what you call it, a century pop. The century pop sort of moved with your punches a little bit because it's somewhat flexible. How would you protect yourself if someone's boxing against you? And century pop doesn't hit back, right? But if someone's boxing or kicking, at you, what would you do to try to keep yourself from feeling a smaller impact? If someone's throwing like a jab at you or something, what would you do?
Dodge it. Or
Okay, so you're going to dodge it. So you might either go to the right or to the left to try to make a miss. Well, what else could you do? Put your hands up. What else could you do?
Bury it.
How do you bury it?
Bury it.
Oh, what's that mean? Oh, yeah, okay, gotcha. One more thing that you can do is that really good boxers, what they'll do is they'll ride with the punch. They'll ride with it, right? So, no, I'm not going to actually fake throw a punch at me here. Don't let anyone see that you're just slowly throw this thing out. Watch what I'm going to do here. As he throws this thing, what I'm going to do is I'm going to ride with it. Now, I'm probably not going to be fast enough to be able to completely avoid it, because he can throw a punch at maybe 80, 90 miles per hour. The most I can maybe do is move my head back at 10 miles per hour. So I can't completely eliminate that impact, but throw it up again slowly. If I ride with it, what I do is I extend the time interval for that force to come to a stop. So like if I ride with it, I'm afraid. I mean, this guy really hurt me, right? So if I ride with it, I can extend the time interval. And so that's another thing, because I probably cannot completely, unless I'm really fast, but if I am constantly sort of riding with it, then I can lessen that one. Okay, and it's a time interval. Okay, so the big time for a small force, if you ride with that punch, and that's what we're trying to show here, is that that person sort of goes back with that a little bit, and that makes that force quite a bit smaller. If you take one of those where you just sort of like lean into it, that force is going to be really big acting during that head, right? So you could definitely hurt yourself. Okay. Now, I'm not going to do the conservation momentum stuff. I'm going to look at that tomorrow. Okay, I'm going to stop. Oh, I forgot this one. When you come in from the outdoors, I often say, stomp your feet, stomp your feet. The idea there is that now what I want is a really small time for my foot to come to a stop. That makes the amount of force acting really big, and that really large force there is enough to be able to remove the mud from the boots, to be able to get that off. So you often will kick your feet onto something. That makes the time interval really tiny, makes that force really big. Applications of impulse momentum. Okay, that idea. Now, I'm going to stop there.